Okay, so as Zlatko announced, I will be talking about streaming DMD and dynamic forecasting, and this is joint work with Zlatko. So the setup is very basic. We assume that we have one trajectory that we have sampled from, and we are trying to approximate the dynamics linearly. So we are trying to find this DMD matrix A. Now I will focus on the case when we have snapshots of high dimensions. So there are more snapshots than the snapshots are longer than there are of them. So the data matrices are very tall. And in this case, we have an underdetermined problem because A is very large and we have a bit smaller amounts of data. And so we usually solve it in this way that we all know. And the problem with having this scenario is that the solution is not unique. So when there is more data than there is the length, this x perpendicular is trivial, 0. But in the case where the snapshots are really long, it's not trivial. So the solution to that is what Zlatko already mentioned, Schmidt's algorithm, which is essentially Rayleigh-Ritz method, which kind of extracts what is in each of those solutions. So the Rayleigh-Ritz method will give us some eigenvalues that are embedded in all of those kind of. Now, for the streaming part, the assumption is that we have streaming data. So we have new snapshots coming in or a batch of new snapshots coming in. And if we want to do forecasting or if we want to do something with it, it is important for us to have this fresh data to embed it in our matrix A. And so what we want to do is we want to take in this fresh information and possibly also discard the old information that might not be relevant anymore. And we want to use the A that we already have. So we don't want to start from scratch, but instead we want to update what we had already achieved and calculated so far. So the main literature for this have been these two papers, and I will focus on Hemati, Williams, and Rowley paper because they address this case where M is much larger than N. I will go through their idea, and then I will point out some improvements that can be made and what we had done. So their idea is to, instead of working with this large very long data matrix X, to find an orthonormal basis for X and Y, and then to decompose X as QX times X tilde. So instead of working with this big X, we would instead work with this X tilde that is also a full row rank matrix. So for instance, we can find this QX by performing SVD and then finding the numerical rank. And then of course, we cannot update the matrix A because we said that the matrix A is not unique. But what we can do is update this Rayleigh matrix, A tilde, from the Schmidt's algorithm. And the idea is to update that matrix. Now, it can be shown very easily that this smaller matrix A tilde is equal to this here. Now, this might seem like a more complicated version, but for doing an update, it's rather simple because what we need to do when a new snapshot becomes available, we have to expand QX and QY, possibly. So first we have to see if it is necessary or not. We check if they're already in this subspace or not. And then this Y tilde X tilde transpose is actually just a sum of yi tilde xi tilde transpose. So when I get new data, I calculate y n tilde x n tilde, and I just add it to this. Now, if I had expanded qx and qy, it will be one element longer, but that's not a problem because the new element of all the old ones will be 0 because it was already in the smaller space before. So very simple. I just update these qx, qy, and then I add something, just one term onto here. And it works well. So this is the same vorticity data that Zlatko used. This is an example when we took 30 data at once and then added one by one, and then did a prediction 10 steps ahead at some point. So here we had like 50 data in total, and then we were making a prediction for 60th step, and this is the true data, this is the approximation, and it's, as you can see, very similar. Now, what are some problems here or modifications that can or should be done? So the first one is that this is an algorithm for adding one snapshot at a time. But that one is easily solvable, and also it is kind of computationally similarly expensive to do 5 at a time or 5 one by one. So that's not a big issue here. The other one is that using Weyl's theorem, we can observe how the largest and smallest eigenvalue change. And we can see that the condition number of this Rx nu, this is the thing, so this is here, which we take a pseudo inverse of, that its condition number is increasing. So I'll show you a picture. This is for one of the examples. We see that the highest singular value is increasing and the largest one is decreasing, so the condition number will be bigger and bigger, right? Then another condition number problem is that in the initial formulation we had yx dagger, so we just had a pseudo inverse of x, and now we have to work with x tilde transpose, and the condition number of x tilde transpose is the squared condition number of x. So again, not a very good scenario numerically. Another one is we have this assumption that we have one trajectory, and so each new y is actually the x that we used in the previous iteration. So the subspace that qx and qy are spanning are almost the same if we exclude the first and the last column in each. So why would we calculate it twice? It's not good also for memory purposes. And so we would want to see if we can somehow have just one Q. It will also be easier to do some calculations afterwards, which I will show. And maybe the main problem here is how to remove the oldest snapshot. So it's not, there's really no way to remove the oldest snapshot here. So as we add on new data, the oldest snapshot becomes irrelevant, but we cannot remove it in a simple way. We can maybe start from scratch and then go this way. Our algorithm proposes that we don't do this kind of orthonormal basis for x and for y separately, but instead that we put all the data in one data matrix S and then perform a QR factorization of this S. So then, if we do that, we will have, since x is just the first n columns, then it will be equal to q times the first n columns of this triangular matrix, and y will be q times the last 10 columns of this triangular matrix. And then the idea is to work with this R1 and R2 instead of X and Y. So this is kind of like a change of basis. And there's also a reason for it. So if we go back and see A, now it was equal to QX transpose QY. If I have the same Q as my change of basis, then this turns just to I. And here, so this part with X tildes is actually just equal to x tilde dagger, just x tilde pseudo inverse. So the idea is that when sending our data off to Schmidt's algorithm, we just send y tilde and x tilde instead of y and x. And so yeah, now the question is, okay, we have this, but how do we update this factorization? And there are some methods already developed for the updates of QR factorization, so it is somewhat simple. If we have new snapshots coming in, we can assume that there's a batch of snapshots coming in at the same time. Then this new data matrix is just the old data matrix and the new columns, right? And it can be rewritten in this way. And this part is actually, so I project B onto the subspace spans by Q, and then I remove that from B. So I have this subspace that is orthogonal to the subspace spanned by Q. And now the only thing left to do is so this part is already orthogonal to this, and this is a triangular matrix. So the only thing left to do is to orthogonalize this one. But since it's we assume that it will be somewhat, short, we just do classical QR of it. And then in this very simple way, we have achieved the new QR decomposition of the new S. And for the removal of data, so now what we have to do is kind of from this R1 that we just have to remove the first few columns. So we will have a matrix that is almost diagonal. It has a bit of diagonal elements. So the idea is to use classical householder matrices or Givens rotations, and then to eliminate everything from below the diagonal, and then that goes into the Q and the modification goes into R. But what is good about this, they're kind of independent, the adding and removing of the snapshot, and we can have a very dynamically changing window. So not only that we can remove the snapshot, but we can also choose how many we want to remove and how many we will add. So we have full flexibility in that. Instead of updating and saving QX and QY, we only update Q, which can be great if you have really, really large data. Instead of working in this large space, Rm times n, we actually work only with R1 and R2, which are in n times n. It is more numerically stable, and it is also cheaper to calculate these residuals that Zlatko was talking about and alphas in the prediction, because there we have some norm of difference, and then if it's the same Q, the Q can exit out because it's an orthonormal matrix. In the case of Hemati, it was different Q, so we could not take it out of the calculation. And so then again, we also moved to a smaller space. So this is the same example that the first Hemati algorithm worked on. Ours works well there too. And we wanted to have an example where we have a lot of, we can have a lot of data coming in. So we used the van der Pol oscillator. Now, van der Pol oscillator is not a very long snapshot. It's just it's of the length of 2, but we did the Hankel embeddings, so EDMD, where we stacked some snapshots. So the length is actually 160. And if we try to do we cannot do a full prediction after, after it had seen some amount of data, we cannot do a full prediction for what will happen the rest of the time. But we see, this is the classical DMD, we see that it does a good prediction for the first couple of moments, and then it drifts off. So kind of, it would be good if we could, get new data up to here and then predict here, and to do this kind of an online version. So we compared Hemati algorithm with our algorithm, and the blue line is the original van der Pol oscillator for me equal to 0.8. The pink dashed line, which you might not see well, but it's perfectly on the van der Pol, on the original data, is our prediction for 1 moment ahead. So we have a fixed size window here, and then we get a new snapshot, remove the oldest snapshot, and then make one prediction ahead. And the orange line, which kind of drifts off a bit, is the Hemati prediction. When we increased me to 2, Hemati prediction gets lost even sooner because it's trailing all of the former information and we cannot remove it. So, but this was just predicting one moment ahead. We wanted to see how much we can predict ahead. And if we do 5 moments ahead, it still does a good job. So it kind of starts to lose it a bit here. And we see that this is 10 moments ahead, 15 moments ahead, 20 moments ahead. So it kind of gets worse. So it's not perfect, but it's good for the local. Then this is the example where there are sudden changes in me. So it's 2, then 1.5, etc. When predicting one ahead with fixed window size or changing window size, so we see the thing is when we're doing prediction, we can test how good our model is because I get new data at some point and then I can see, okay, was it good or was it bad? So here, if we would get like big errors for 10 times in a row, then we would say, okay, something has changed in the dynamics, cut off a lot of the old data and just keep more of the fresh ones. So here, this is just prediction 1 moment ahead with a bit more complicated van der Pol. So there's not much difference, but if we do prediction 5 moments ahead, and the only thing here that we're doing is like, this is the example where we keep a fixed window size. So even if the error is bad, we just stay with this window size of 100. And here we do this thing of like cutting the window short and then expanding it again. So it works better in this case when we have decided to adapt the window size according to the errors that we've had with our prediction and the real data. And another example, this is again 1 step ahead, but this is without using all of the modes. So as Zlatko was saying at the end of his talk, or actually in the middle somewhere, we can also like try and use less modes with the, and these were selected by looking at the residuals. And if we had a changing window size and selected modes, but had a fixed threshold for which modes I cut off, it was not doing very well because when I cut off the amount of snapshots that I have, probably what happens is that just my errors will be automatically larger. So instead, when we used an adaptive threshold that changes when the data is cut short, it worked, it performed better. So this is fewer modes and an adaptive threshold on which modes I take, and it works good, the changing window size and everything. Okay, so just a conclusion. It's good to be able to have this changing window size, not just for the tangentiality presumption, but also for memory-wise, because also when I was doing some examples, I would just run out of memory with the Hemati version because it keeps all of the data in it. Even though these two things are analytically the same, which Hemati uses this version, it can lead to problems in finite precision dynamics, and 1 orthonormal basis is better than 2. Thank you.